Okay, differential equations. You can see starting a new chapter, chapter 3. Here's our learning target. I can solve exponential growth and decay problems. If this sounds familiar, it should. You've done this before. So, as we're looking here, P of t in general is going to represent the amount of something. In general, P has been used because it could represent a population. But what you're going to see is P is going to be assumed to be positive. That's super important, very important. You know, whether we're measuring a population of people or animals, bacteria, or dollar amounts, as you'll see in just a little bit, we're going to assume that we're always talking about a positive amount. And the rate of change, wow, that's what calculus is all about, isn't it? dp dt, how the population is changing with respect to time, is directly proportional. That means there's some fixed constant that you're going to multiply to the population. So what we're seeing more or less is here's that constant that we're talking about. When you're directly proportional, it's some fixed number, could be positive or negative in that regard. So dp dt is equal to k times p of t. Well, tell you what we're about to do. We're going to separate our variables. Wow. Can divide both sides by p of t. Simultaneously, let's multiply by kt. And then as we integrate, as we're going to go ahead and do some integration here, you can see where we're going. The left side, remember P of t is positive. It's a positive amount. So what's the antiderivative of 1 over P? The ln, and we don't need parentheses or absolute value around it because our population is positive. On the right side, we could say, well, we'll have kt. We're going to take our antiderivative with respect to t. But here we go, add some pesky little constant right there, right? And ultimately, what we did, and we derived this even in Calc BC, we took it a step further and we said, well, how about we find what P of t really equals? And how did we go about solving for P of t? We exponentiated. So we take e to the left side. We could continue up here. E to the left side, thankfully, is just a P of t. On the right side, we'll have e to the kt plus c, but that's also times e to the c. And e to the c, of course, is just some constant. I'll call that c2. And guys, this probably is looking very, very, very familiar at this point. We just follow it up with one additional thing. If I wanted to find that constant, if I let t equal 0, well, the left side would be p of 0. The right side would be e to the 0 power, which is just a 1. C sub 2, that second constant, is your initial population. Wow. So what you would have done back in Algebra 2 even, without a doubt, you would have spent time just saying, hey, P of t was equal to P of 0, your beginning population, times e to the kt. Now, to be fair, a lot of times we'd even write that as a subscript. Maybe you've seen it written more that way, that P sub 0, that would be your initial population. Yes?
This is very similar to like a continuous population.
Yes. Yeah, there are definitely connections to interest as well. You're right. Good. So here's the cool thing, guys. Once we've seen this, we're going to say, you know what? Let's just use this formula. And ironically, as we're getting to that, you could very much see that I'm not asking you to go ahead and solve a differential equation in this section, really, as much as solving exponential growth and decay problems. Now, it says an account earning 5% interest. Now, 5% interest as a decimal would be written as 0.05, and that's your growth rate. That's your growth rate. So I'm going to say, actually, K would equal 0.05. Wow. How about that? And they're saying an account is worth $48,000. What was it worth 5 years ago? What was it worth? Now, we're assuming, Kunz just asked a second ago, is this compound continuous interest? Here, we're just going to say that we're, officially having like an annual rate of 5%. Okay, 1 second. Ultimately, what we're trying to answer, guys, is what was our beginning amount if we go 5 years in the past? If K is 0.05, T would equal 5, and we could go ahead and just solve for P sub 0. So crazily, you could say P sub 0 would be 48,000 divided by our E to the 0.05 times 5, and of course we could easily multiply that out. But look, you don't even need to use your 89. I know sometimes kids are quite happy to, just go ahead and, use their 84s. I think we're so much used to them. So we have 48,000 down below. I'm going to make E show up, hit second E, and we'll say 0.05 times 5. And rest assured, in just a click, you can see going to the nearest penny, we'd have 37,000. 382 was it, I believe? I think that's right. And 44 cents. Let's double check that. Hope my memory was good. Yep. Rounding to the nearest penny, I took that 43 and I bumped it up. Okay, so you could get questions just like that. And, like as Kunz had mentioned before, it's, really like the PERT formula right there. We're assuming compound continuous growth here. All right, so let's real quickly take a look at this next problem. It says a culture initially has P sub 0 bacteria. Wow, we don't know the specific. And at T equals 1 hour, the number of bacteria is measured to be 1.5 P sub 0. Determine the time necessary for the bacteria to triple. And you think, well, wow, how could I do that? Well, look, you could very quickly just jump to this standby. You could say P is equal to P naught e to the KT. I certainly don't know what I'm starting with specifically. I'm not given an exact number of bacteria. It's just in general. But I do know that I'd like to say after 1 hour, after T equals 1 hour. And time, of course, could be measured in this regard to be different units. It's in the context of the question. The big question right here is, could we go ahead and make this information help us? We want to find out how long it takes to triple. You might remember in calculus, we did something a little bit different than you did in AMA. In accelerated math analysis, you might have solved for what K was equal to, right? And you could have stored that as a decimal. You could take a natural log of both sides and find out what K really is equal to. But it's just as good to know what E to the K equals. If you know what E to the K equals, dare I say that might even be better. That can sound so funny. You could think, whoa, I remember doing that years ago, but hopefully you remember from in Calc BC, what we were talking about was this, that if you go to this general formula, here's your E to the K. Oops, let me get my highlighter back here. Here's your E to the K. And here's your E to the K. Do you see what I'm getting at? So you could say, well, wait a minute. The formula that I'm really looking at would be 1.5 bumped up to the t. Look at that. Because e to the kt is really the same thing as e to the k raised to the t power, in other words. I don't know about you. I think that kind of looks kind of nice when you see it in that regard. So that's kind of cool. Give me 1 second. I advise you to solve for e to the k, and now they're going to say, how long will it take to triple in your growth? Well, what you're saying is, I want to end up with 3 times what I began the problem with. Even though I don't know the exact specific number, I could still figure this out. I can divide by p sub 0, and this will wipe out, and that will wipe out. And now what? Well, now you just have to go ahead and solve for this. Ooh, good algebraic reminder. How do you solve for t in this regard? Take a natural log. How about that? We'll take ln of 3 equals ln of 1.5 to the t. We can bring that t down. And my word, now we just divide by the ln of 1.5. And real fast, we can get that to work out. Ln of 3. Well, you can't subtract here. That's not the subtraction property. See, and that's worth talking about. It's about 2.7 hours roughly. Yeah, the subtraction property would be ln of a over b. So yeah, we got to be careful about that property, right? Okay, one more problem, and that's on the back. Half-life of carbon-14 is 5,600 years. Wow. A fossilized bone is found to contain 1,000th of the C14 found in living matter. Estimate the age of this fossil. Wow. First off, I do want to say that we could solve for e to the k. When they're giving you this half-life, you're saying, look, I don't know exactly what we're starting with necessarily, but I do know it's going to take 5,600 years for our mass to become 1/2 of what it was, right? So I've got my t equals 5,600. By the way, I hope you can see that you can divide out your p's, p sub zeros. And how could I solve for e to the k? How do I get rid of this 5,600? Yeah, you got to raise it to the 1 over 5,600, right? You'll do that. And that, honestly, is what this thing is going to become. So when I come back here and I'll say, well, I've got p sub 0 e to the kt. Here we go again. We can say that e to the k, guys, that e to the k I've got right here. And it only takes a moment for kids to hopefully make that connection that it really becomes 1/2. Now the t can actually come up and, multiply to t to the 1 over 5,600. Look at what we have right there. Okay, so to finish this problem up, they're going to say, you are dealing with a mass that's 1/1000th of what you would have begun with, of the original. And could you solve for t? Well, divide this out, and I think you can see pretty quickly we're going to take an ln of both sides. And as you take the ln, guys, you're going to be able to drop this power down. So you'll have t over 5,600. And now you just clean it all up. What you got to do to solve for t, first you could divide. You can divide by that. Oops, writing kind of fast, trying to save us some time. And then you're going to multiply by 5,600. This left side, you'd get 9.96, something like that. And then you multiply both sides by 5,600.